electrical power and drive systems. Got a handout for you with board notes. Most of them I will have. In fact, I think I've got something for just about every week on this course. I don't tend to. Gemma's probably already got all these, but you might have lost them. I think we're missing someone. Yeah, oh, I know. That's Lewis. Lewis did tell me he won't be here. Right. So, the assessment of this module, which is the most important thing to you, is in the form of 3 parts, 2 assignments written, and thirdly an examination of 2 hours duration, sometime in May, possibly early June. I don't know the date off the top of my head. It has been sent to you, but I'll confirm it near the time. Assignment 1, analyse and critically evaluate methods of AC and or DC motor control. Just for you, Gemma, you ain't got to do the assignments again anyway. I think you know that. So give you a bit more time to have a go at the calculations that are important for the exam. So there's no harm in that, yeah? Assignment 2, investigate and critically evaluate further applications of power electronics. Okay. Now, I do some teaching around those topics, but then there's research for you to do to dig deeper into the topics and write a report about a given system in both cases. I think in both assignments I give you 2 options to choose from as to what you talk about in terms of those aspects. So there's 2 different types of applications for motors, so you pick one of them to apply the motor selection methods to, and then in the second one I give 2 options in there of 2 different topics of power electronics that you can choose one of them to write about. And then the examination is all around the 3-phase power distribution systems and the analysis of them, transformer analysis and such. Okay. Now, there is a fair bit of maths and calculations in the examination for this module, and as we go through the weeks, they aren't particularly difficult. There's Ohm's law, power calculations, there's some trigonometry, there's a bit of work with complex numbers, okay, but nothing particularly difficult in terms of complex formulas that I see in Adrian's stuff that kind of frighten me off a little bit in that topic. But if you don't understand the underlying electrical concepts, it's sometimes a bit difficult to know what calculation you've got to do. So there isn't a huge list of formulae that you need in the exam, but you need to understand the electrical principles so you know what's the right calculation to do. So plenty of practice. I go through a topic, and then towards the end of a session, most weeks I've got a set of tutorial questions for you to start on in this class, carry on during the week in between, and work solutions will be put on bright space for you to look at as well. And I believe every one of them I've got a set of work solutions. Alright? So you'll see a bit more as we go along. Okay? Now, what I'll tend to do is in the earlier sessions where there's a situation where there's an assignment running as well as us doing calculation problems, we'll kind of split the class into the analysis of power systems, the bit assessed in the exam, and the other half of the session around the assignment. Okay? And then when the assignments have been issued and done and dusted as such, sort of halfway through-ish, maybe a little bit more, we'll then devote all of the teaching time towards calculations. And certainly when we come to look at the transformer modelling, we start to apply that to a practical transformer on the rig there as well. So it's not all kind of dry and just doing imaginary calcs. We actually prove that transformer model by modelling the transformer on the rig. Alright? So, enough about the module in a whole, I want to talk about power in single phase AC circuits. So we got a diagram there. It's got a single phase load supplied by sinusoidal voltage. Okay, now I want to get clear some terms. If we talk about instantaneous values of current or voltage, because in AC systems those things are changing 50 times a second, we're going through this cycle, so they're constantly changing. If we're talking about a value at an instant in time, we use a lowercase v at time t or a lowercase I. And it is important when you write your exam answers that you distinguish between instantaneous values, little case I, little case v at time t, and what's called the peak value, I max, V max, that goes in front of the sine. The peak value of the sine wave. Our capital letters V and I. Alright? So we got Vm as peak voltage, Im as peak current. This funny looking thing like omega, like a W, is actually omega, lowercase omega, and that is the angular frequency in radians per second. Okay, anytime you're working with values that include omega, you must have your calculator in radians mode. We're doing sine, cosine functions, etc. Yeah. For most of this module, we'll be working with our angles in radians. So, a little bit of dip into degrees, but most of the time, radians. And that's because omega is equal to 2 pi times the frequency in hertz. That's where it comes from. So we can always get, if we got our frequency in omega form, we can always get it in hertz form by remembering that omega is equal to 2 times pi times f. Yeah? And the pi in there means any angle involved has got to be in radians. Alright? So we can express an instantaneous voltage as the maximum voltage times the sine of omega t plus or minus a phase angle if it's got a phase shift in it. And a current I at time t is the maximum current times the sine of omega t plus or minus omega 2. Could be a different angle. We're going to look later where we got current and voltage out of phase with each other, and so they've got different angles. Right, you should have already seen voltages and currents expressed in that maximum times the sine of omega t plus or minus a phase angle form earlier on in your studies at some point. How long is it since you've done your HNC, Roger? 10 years ago. So does that come out to you at all or not? Yeah, because yeah, I know you're mechanically biased in terms of your job, aren't you? Yeah. So moving on from that, power in single phase AC circuits. So we are applying this voltage waveform V at time t. It's going to cause a current to flow IT. It follows that we could calculate the instantaneous power at any point in time by multiplying the instantaneous current by the instantaneous voltage. So we can do Vm sine omega t plus or minus the angle times Im sine omega t plus or minus the angle. And that way you could calculate the instantaneous power at an instant. Right? So that's a fairly simple application of the formula power is equal to I times V. Yeah, and the units are watts. Yeah. So, we're going to now talk about how power, and there's 3 different powers in an AC circuit. First of all, we're going to look at what's called active power. Where a load is purely resistive, the current and voltage are in phase, and all the power from the generator is converted into useful power. So, if we look at this circuit, that is a simple R, and we're applying a voltage. We've got a current flowing, and the current and voltage, this is the phasor diagram. So there's the voltage in blue, there's the current in green, and they're at the same angle. And the convention is that 0 degrees is represented by left to right on the horizontal axis, yeah, in terms of phasor diagrams. We might drift a little bit away from that when we talk about 3-phase systems later on, but generally 0 degrees is that left to right on that axis. And therefore we have a power, an active power phasor there that is also horizontal, and it is P in watts. Okay, we can do P is equal to the generator voltage times the current, or we can do I squared times R, or we can do the generator voltage squared divided by R. They're the 3 power formulae that you ought to be useful with in terms of P is equal to I times V, P is equal to I squared times R, or P is equal to V squared over R. Yeah. The difference in notation here is we're just talking about the generator voltage as EG. Right? And I'll try where I can to use the convention of, if that's a source of voltage like a generator or a battery, I'll use the term E for EMF. But not all textbooks do, so you have to kind of get used to there being differences. Whereas if I talk about the voltage dropped across the load, I'll use the term V, or potential difference. All right? So if I graph those 3 items, so the blue graph is the voltage over time. Yeah. The red one is current, and the yellow one is the power. So I've said that this yellow one is the red one times the blue one through the whole cycle. And you can see that the power, let's just block that out in green, is all above the line. It's not constant, but it's all above the line. Yeah? And over that period of time, the average would be around here somewhere. Okay? But it's all active power being used by the load to generate heat or motion or whatever other form of energy you want to convert it into. Yeah? That's if your load is purely resistive. So we've got active power, the symbol's P, the units are watts. Okay? Yep. And there's a note here that for correct calculation of AC power, the values of EG and I are RMS values. RMS standing for root mean square. And what the root mean square value is it's the value of that waveform of voltage or current that would give the same power as the same level of voltage in DC. So coming out of those sockets over there, 230 volts RMS would would give the same power in the same resistor as 230 volts DC. It's a straight line value given the equivalent power, right? And it's equal to peak voltage of a √2. So if you looked at the peak voltage of coming out of that socket there, like 330 volts RMS is that 330 of a √2. And the same with I, peak voltage of a √2, peak current of a √2. Yeah. So, having considered what happens with a purely resistive load, we're going to consider something now that's not achievable wholly in a real circuit, and that is a purely inductive load. That curly line there is a symbol for an inductor, L, okay? An inductor is a coil of wire. So whilst that'll have a relatively low resistance, a real inductor will always have some. But we're considering an imaginary inductor that has no resistance whatsoever at this point in time. What we get from that is a current and a voltage that are 90 degrees out of phase with each other. So on this diagram, I've used blue for voltage. So there's our voltage, EG, okay, and that produces a current that is in red on our diagram down there. It's 90 degrees out of phase with the voltage. Yeah. And we talk about angles go round in an anti-clockwise rotation. So in that sense, the voltage here is ahead of the current. Yeah, it lags. So current lags the voltage by 90 degrees. We could equally say voltage leads the current by 90 degrees. Anyone remember the word I use to remember which way round? Civil. Yeah. C-I-V-I-L. Inductive circuit, current is after or lags the voltage. And that's useful in any of the calculations you do. If you know whether your circuit is overall inductive or overall capacitive in nature, you can check that you got your answer right, because it's ever so easy to drop a negative sign somewhere accidentally in your calcs and get the angle the wrong way round. Okay? So it's well worthwhile remembering that little check, and when I do example calcs on the board, I'll point out to you where that check could come in and where you can make use of it. Equally, in a capacitive circuit, as you see in a minute, we'll find that current leads voltage by 90 degrees. All right? So, what we get with a pure inductance is what's called reactive power. Use a symbol Q. So we've got this QL measured in VAR, VAR, all lowercase, stands for volt amps reactive. Okay? Now, the inductor is said to absorb reactive power from the source. Now, if we look at this diagram, here's our voltage starting at 0, blue line there. Red line's the current. It peaks in time after the blue one, which shows us lagging. A lot of students get in a muddle with that. They think because the voltage looks as though that's behind it, that's lagging. But time goes that way, left to right. Yeah. And if we then calculate the power instantaneous, there it is. that green line there. We've got half of it above the line, half of it below. There's an area below, area above. Area below, area above. So, once in what's given in one breath, it's taken back in the next. No real power is being used because the inductor's charging up in one half cycle and giving everything back in the other half cycle. Causes a current to flow, but doesn't do any useful work whatsoever. So the waveforms show that each positive power pulse is matched by a negative one, meaning no electrical power is converted to useful power. Inductive loads are said to absorb reactive power, QL, from the source. Yep. All reasonably happy with that up to that point. Yeah. Okay, a little bit more about it. We've got this, so I've got a phasor diagram here now. There's my voltage. I didn't want that in green, did I? I had the voltage in blue, I think. E, G. There's my current in red. Okay. We've also got a power work on a power phasor. QL that's considered to be positive in angle. So there's the arbitrary 0 degrees, and QL makes a vertical component upwards, positive 90 degrees. So we can find QL from data in a number of ways. From the generator voltage, if that's the only load, times the current. So again, that's a version of P is equal to V times I, except we're not talking about P, we're talking about Q. You can get it from I inductor squared times the inductive reactance, XL. I'll go into XL in a minute. And you can get it from the generator voltage squared divided by XL. All of those are measured in VAR, and XL can come from omega times L, where L is the inductance in henries, or alternatively 2 pi FL, because omega is equal to 2 pi F. Alright? So depending on the information about the circuit you're given, you can find out, if you know the current through and the reactance, you can calculate Q. If you know the voltage applied and the current, you can calculate Q. And if you know the generator voltage or the voltage applied and the reactance, you can calculate Q. Yep. Alright? Or not? XL is inductive reactance. Yep. The overall term for opposition to current flow in an AC circuit is Z, impedance, in ohms. Yeah. we've got R as also in ohms, XL as in ohms, and XC is also in ohms. But that, and that are all complex values. Yep, the angle's important. Yeah, yeah. And changes with frequency as well as a key point. Because once you involve any component that's reactive, that value XL is going to change if frequency changes. Yeah? And more about that later. Okay, so that was reactive power inductive. Now reactive power capacitive. So if we could have a per capacitor without any resistance, again, not wholly achievable. We can probably get a bit closer to that than we can the per inductor, but we can't get all the way there. Okay, we apply in this case a generator voltage, e.g. look at a current flow I at time t, and this time we got a phasor diagram where the voltage e.g. is in blue and the current in red this time leads the voltage by 90 degrees. Yeah. So where the load is purely capacitive, current leads the voltage by 90 degrees. There it is in civil. Current's ahead of voltage on the capacitive side. All right. We get a QC that is minus 90 degrees. QC in var. There's our 0 degrees. Alright. Again, the reactive power is measured in volt amps reactive. And if we graph the two waveforms and multiply them together, we get a power pulse above the line, followed by one the same size below, and then another one above the line, and another one below. If you compare them with this one, they're the opposite way round. So where it was above the line here, that's below the line in that one. So they work opposite to each other. Yep. So again, later on, we'll look at where we have both components in the circuit. And the waveforms show, again, that each positive pulse is matched by a negative one. So again, no electrical power is converted to useful power. But we say that capacitive loads are said to supply reactive power to the source. So when an inductor's pulling power from a source, reactive power, a capacitor will be giving it back. When a capacitor is drawing it, so when that's charging up, the inductor will be given some back. So they work with each other to offset each other, as you're going to see later, and that's the principles of a topic called power factor correction, which will come in a bit later. Alright? Everyone got everything they want from that slide? Incidentally, alongside the videos, I also PDF these slides that I've written all over, so you can get a copy of them as well, and I put the blank ones on the website as well, so if you miss a blank set or want to get them off on a week when you haven't been here for one reason or another, you can. Alright? So, here we are again, reactive power. It's got the phasor diagram with the current I leading the voltage E by 90 degrees. There's QC pointing downwards. That's in VARs. We can calculate that from the generator voltage times the current squared times the capacitive reactance, XC, or the generator voltage squared divided by XC. Yep. That must be, what you must get from this is, if you're going to use one of them formulas, it must be that voltage is isolated and all of that voltage is across just that component. Yep. Which usually ain't going to happen, because you're usually going to have some capacitance and some resistance as well, maybe some inductance on top. Alright? But if you can isolate it, you can use those formulae. And that's where XC is equal to 1 divided by omega C, or 1 divided by 2 pi FC. So also, these two values, XL and XC, work opposite to each other as well. Because if you increase frequency, 2 pi FC is going to get bigger. The overall reactance is going to get smaller. But so as you increase frequency, the reactance of a capacitor gets smaller, but the reactance of an inductor gets bigger, and vice versa. So in terms of their impedance, they work opposite to each other as well. Yep. And you'll see that a little bit better when you start to have a look at circuits that include both components and a resistor as well. Alright? Omega is angular frequency and the units are radians per second. Yep. So it's, if you think about omega being equal to 2 pi times the frequency in hertz. Frequency in hertz, how many times it goes round a second. Yeah. 2 pi is how many radians there are in a complete circle. That's a complete circle. Frequency is 50. So omega for 50 hertz is 100 pi. Yeah. That gives you 100 pi radians per second. The hertz is revolutions per second. Yeah. Alright. Any questions or issues on that so far? Okay. Now, busy slide, I know, but it kind of trying to summarise the distinction between active power, at P measured in watts, and reactive power. One cannot be converted into the other. They function completely independently of each other. They can be treated as separate quantities in electrical circuits, but they all interact. Both place a burden on a transmission line that carries them, i.e. they both produce a current. More about that later, but remember, the reactive power does no useful work, but it draws a current. Yep. Active power produces a tangible result in the form of work done, heat, mechanical power, light, and so forth. Reactive power does no useful work. It represents energy that oscillates back and forth between the source and the load. A large system, such as a factory, represents a large active reactive load in the form of heaters, motors, etc. To draw reactive loads to sustain the magnetic fields in motors and transformers, as well as active loads to provide heat and mechanical energy. So you can't get away without having some reactive load, because a motor is a reactive load by its very nature. It needs that magnetism produced in the coils for it to work. Heaters are often coils of wire. They heat up. They've got a magnetic effect. But when relays, transformers and so on, all coils of wire are going to be a reactive load. Okay? This leads us to consider loads that absorb both active and reactive power and how they work together. So that's where we're going to move on to now. Yep. So, real and reactive power combined. We're going to consider now a load where we've got resistance R and inductance L in parallel. Yeah. So we've got a current flowing here, IT. We must look at these slides, and we get an IR down through the resistor and an IL down through the inductor. Okay, and voltage blue. So there's the voltage phasor. Yeah. VG in blue. In this case, you'd say that voltage is the reference phasor, and I'll put that at angle 0 because it's applied to both the resistor and the inductor. So we're holding that at 0. Then we can talk about the resistive current. I'll do that in green. There's the resistance current, remember, in phase with the voltage. Yep. And then we got our reactive current, 90 degrees downwards. See, IV, IL. I got that the right way round. Yeah. I got my current lagging the voltage in a reactive circuit. An inductive circuit, sorry. Yeah. So, the actual current that flows here, IT, the total current being drawn from the generator, comes from us completing this parallelogram of this phasor diagram, and is in there. There is the main I at time t. Out of phase with the generator voltage, okay, out of phase with the resistor and the inductor current, but that's the overall phase angle of that current flowing there. Current IR is in phase with the source voltage, while IL lags by 90 degrees. Okay, so what we'll sometimes come across is the IR being, I would say, is the in-phase current, or the horizontal component of this resultant current, and the IL is the vertical component, and that's a negative vertical component. It's pointing downwards. Yeah. So the current drawn from the source lags the supply voltage by this angle in here, this angle theta in here. Yeah. And if we go along and plot those two values, so the blue line is the applied voltage at angle 0. The current in red is the overall current at angle theta away from the voltage. So this angle in here, between those two, that in there, is theta. We then get a power curve. If we multiply the two waveforms together, that's got, in this case, quite a lot of area above. That is where useful power has been converted, or electrical energy has been converted in useful power. And this bit down here being less using overall reactive power and being wasted. So the two positive areas represent real power in watts, and the two negative portions represent reactive power, QL, volt amps reactive. Right? So, we think about the powers combined. So I've included the voltage and current phase diagrams as well. But we've got QL pointing upwards, QL, VAR. I'm just going to move that a little bit because I want to. And we've got P in watts down here. Alright? And in a minute, not too sure when that come in now, we're going to consider the combination of those two, which again is the completion of a parallelogram. We'll talk about that phasor up the middle there shortly, which is the third type of power that we need to think about. Alright? So, magnitude of the current I drawn from the source can be found using Pythagoras theorem from this triangle here of currents. Yeah? Because we know, if we know IR, that distance along there, and we know IL, that distance down there, we can say I is those two currents squared, all square rooted, using Pythagoras theorem. Should have learnt that many years ago in high school. Yeah. So the magnitude of the angle depends on the value of the inductor. Because if we increase inductance, remember XL is equal to 2 pi FL. So if we increase the value of the inductor, inductive reactance is going to go up, Q will go up, and that angle will steepen. And the overall current drawn from the supply will be bigger. So the bigger the inductive load, the more current you're going to draw, but the more power you're going to be wasting, because them bits underneath on that on this graph will become bigger. Yeah. So the bigger you make that angle difference, the bigger these two little bits down the bottom here become. Right, and that'll be apparent in some calculations eventually. Alright, consequently, the larger this angle is, the greater the current required to produce a given amount of real power. So all this altering of XL doesn't affect P at all. That is fixed by the resistance value, and it doesn't change. So you might be drawing more current because this angle's increased down here, So the overall current being drawn from the generator is increased because that current has increased, but this current is still the same, and the length of that power line is still the same. So you're drawing more current for the same useful power being used. Not good. Yeah. So we got more about that shortly, but that's how that works. So more inductance we got, the steeper that angle, the more current we draw from the supply, but the useful power doesn't increase, stays static. The only way we change that is by changing the value of that resistance. Okay, everybody happy with that? So, finishing off these different powers now. If we look at we've got power on the horizontal, P, along here, in watts. We've got QL, horizontal upwards, in var, and we complete the parallelogram, and up the middle we get another value called S. S is apparent power, and it's measured in VA, volt amps. Yep, you'll always see transformers rated in VA. Yep, because you always rate them on the apparent power. They're volt amps, because they are naturally in an inductive load, and it needs to be considered that they are that. Okay, so again we've got this power triangle with P on the horizontal, Q on the vertical, and S on the hypotenuse, and we've got this phase angle theta between the two, and the magnitude of that angle in that triangle and in the current one is going to be the same. Exactly the same angle in degrees or radians. Right, so we can calculate S from the applied voltage times the total current, and from the power triangle in forms of Pythagoras theorem, the square root of P squared plus Q squared. Depending on what information you're given, you can find out what the apparent power is. Forms a triangle with the real power that is the same angle, the angle is the same as the lagging current produced by the circuit discussed earlier. Yeah, it's going to take a little while for all these kind of principles to sink in, but we're going to be doing quite a lot of these calculations around S, Q and P anyway, so over the weeks you'll get used to it. Isn't that right, Gemma? Yeah. Alright, so far? Yep. Yeah, the apparent power gives you what current is going to draw from the source, the generator or the power supply. Yep. That includes the portion that is delivering the magnetism to magnetize the transformer core, as well as the P part, that's the watts that's going to do work. Yep. But ultimately, as a consumer, and the supply authority, you'll make sure that if you're a large inductive load, that you do something about decreasing that angle, because it's got an impact on the transmission lines delivering the power to your load. A bit more about that later. But they have a way of penalising you if you've got bad power factor. So, reactive loads and power factor. Many reactive loads on the system that require reactive power Q to set up magnetic fields, which include motors, transformers, heaters, welding plant and so on. Okay. Now, if you've got a high reactive load, high Q, it means supply lines have to carry more current at a given voltage to provide a given amount of usable power. So we've got this given amount of usable power on the bottom line. Yeah. And the more Q we have, the bigger the apparent power, and hence for the same voltage, the more current we're going to draw. Yeah. So if we consider both those two situations as the same voltage and the same real power, the two apparent powers are different. Removing that angle, if this line is the same length, means the blue line must be shorter than the black one. Therefore, given the voltage is the same, the current in this one must be smaller. So the more you can reduce that angle, the less current, wasted current you're drawing off the supply. So lower reactive load means less current is carried in the supply line to deliver the same amount of usable power watts. The S line of the triangle is shorter. Yeah. So if we look at those two triangles again, and we say something like that as low power factor, they quote power factor as the cosine of that angle. Yeah. So the bigger that angle, the lower the cosine of the angle will be, because the cosine is 1 at 0 angle and 0 at 90 degrees. So as you move that way, you actually get a lower power factor rating. Higher power factors as you approach unity. So ideal would be 1, but they don't try and achieve that. There's a number of issues around that. One would be the cost would be prohibitory in paying for the capacitance to do it. And also you get in danger of getting in a resonance situation if you make your capacitive inductive reactance equal. That's not a situation you want to be getting into on mains voltage systems. Alright? They go some way towards reducing from a situation like the left-hand one to try and get it closer to the right-hand one, because you're reducing the amount of current you're drawing down supply. And we can get power factor is P divided by S. If we look at that in terms of the angle, cosine is adjacent divided by hypotenuse in a right angle triangle. Yeah, so power factor is cos theta. Yeah. And cos theta of 0.6 is poor. I don't know what they aim for, but I wouldn't have thought much more than about 0.9. Yeah. Yeah, they have big places. Your place probably got lots of automatic power factor correction to try and maintain that, haven't they? Yeah. Because you're mechanical, you aren't too au fait with it, but they have big capacitor banks that switch in and out to try and... Yeah. Yeah. Because they do deliver electricity to the grid when you're not in campaign as well, don't they? Or not? When they're in campaign they do. So if they're not using all of it, Oh, okay. So they don't run that plant when you're not in campaign. Okay. They might do. Would they do that in a situation where there was an emergency, like the big generator station went down? Would they? They wouldn't be able to. Okay. Oh, okay. You can't do that. Oh, okay. So that's me misunderstanding something I probably heard in the background. Yeah. Yeah. But you do. Yeah. Because they got an anaerobic digester. Is that why? Yeah. 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 You're not going to get one of them at Canton. Yeah. Oh, okay. Yeah. Right, implications of poor or low power factor. Transmission line, right, your cables hung up or buried in the ground, can only carry a finite amount of current according to their size. Because low power factor results in more current being needed to produce a given amount of useful power, it means that less useful energy can be transmitted by that line. So if you've got poor power factor, you can only draw 100 amps, that's the maximum for the current. You're going to transmit less useful power if the power factor is poor than you would if the power factor was good. You all get that? It's going to draw more current in that situation on the left than you are in the situation on the right. So it leads to supply companies that own the transmission lines penalising consumers for poor power factor through their electricity tariffs. This is done by measuring the maximum demand, S in kVA, and basing the electricity price upon your maximum demand. So they take a reading of S every so often over a billing period, and then the price of your electricity is based on your maximum demand for current, based on the maximum S. So if you have poor power factor, at the time when they take a maximum reading, you get penalised in your bill for that particular billing period, which is probably quarterly, I don't know. I mean, I've got some figures on the next slide, but I don't know how old they are. They might be well over date. But typically, at some point in time, maximum demand charge 230, 400 volts. For each kVA of maximum demand in each month, they're charging like 820 pence, so £8.20 for each kVA of maximum demand. So if you can get that down, you're paying less. Yeah, and it depends on the time of the year as well. But so you got unit charges as well as maximum demand charges. So if you can keep your maximum demand down by keeping your power factor good, then that's better. Now the issue comes when you've got plant that's switching off and on load all the time, big motors starting up and stopping, your power factor is constantly moving. So that means you have to have automated power factor correction. It's measuring the power factor and switching PFC capacitors in and out accordingly to try and maintain a good power factor. So it's not a topic. I certainly don't understand automatic PFC. I've never had anything to do with it. But I do understand the principles of putting capacitance in the circuit to counteract the inductive load. What? Has a little black box, yeah, that goes in there, one round and round in there and comes out there. The old boy where I used to work when I first started, that's what he used to say about a little... If you asked Vic, Just give him bridge rectifier and say, what does that do? But they used to say, well, you put AC in there, that goes round and round inside, come out there as DC. So he knew what it did overall, but he didn't know diodes. If you asked him to talk about thermionic valves, he'd have run on all day about them. But I mean, he's about 10 years beyond retirement age when I was an apprentice. So it's a real old world firm run by a lot of old people that were sort of stuck in their ways, really. But he was a clever man in his field. But he didn't understand modern day electronics that well. So, do you? You do you? Yeah. Would do. Yeah. Yeah. And that is the end of my notes for today.